When trying to solve equations that happen to have multiple logarithmic terms in them, there's really two main strategies that you can use to try and solve those. One of them would be to use the one-to-one property, which should sound reasonably familiar if you've already watched the video on how to solve exponential equations when there's two exponential terms. And it is very much the same idea, because at its core, the one-to-one property is going to mean the same thing each time, and it's basically just saying if you have one property on each side of the equal sign, 1 to 1, and their bases are equivalent, then you can just set whatever those bases are going to, whatever those bases have with them, equal to each other. In exponential form, that's setting the exponents equal to each other. In log form, that is simply taking whatever you are doing the log of and setting those equal. Meaning, for example, if you had the log base 4 of x is equal to the log base 4 of 2, the idea would be I only see one log term on each side of the equation, there's nothing extra going on, and they are both log base 4s. And so since the bases are equivalent, we can basically just ignore them and set what they were each taking the log of equal to each other, meaning the answer to that equation would simply be that x is 2. That's the idea of the one-to-one property. Sometimes we'll be able to use that, sometimes we won't. To begin with here, let's take a look at an example where we are actually able to use that. Let's look at an example of the natural log of x plus 4 plus the natural log of x minus 4 equals the natural log of 6x. Now, as it stands right now, this is not ready for a one-to-one property, because it's named 1 to 1, not 2 to 1, and we've got two natural logs on the left side of the equation and only one on the right side. But if we think back to our properties of logarithms lesson that we did earlier, we know that we could take those two logs on the left side and condense them or combine them into a single natural log. There is addition between those two logs, and addition between two logs condenses into multiplication, meaning I could rewrite the left side as a single natural log of x plus 4 times x minus 4. And then that's equal to the natural log of 6x. So we need to go ahead and take x plus 4 times x minus 4, and that would be foiling, right? We're multiplying two binomials together. X times x would give us x squared. X times negative 4 is negative 4x. Positive 4 times x is positive 4x. And positive 4 times negative 4 is negative 16. If we clean up a little bit there, negative 4x and positive 4x would cancel, meaning we really just have the natural log of x squared minus 16 equals the natural log of 6x. And what you'll notice is now we have a single natural log on each side of the equation and nothing else extra happening, which means now we can use the one-to-one property, being as they are both the same base, log base e, because remember that's what ln, the natural log, represents, is log base e. We can set what they were taking the log of equal to each other, meaning we would have x squared minus 16 equals 6x. That would be a quadratic equation, which means I do still have a little bit of work left here, because we either need to factor or quadratic formula would be the two most likely ways you'd want to solve this. You could also technically complete the square, but I think generally factoring and quadratic formula are the two more common options used. In either of those cases, we need to get it equal to 0. So I would probably subtract 6x over here, because that seems like the easiest way to get everything on one side so that we can have this equation equal to 0. Like I said, It is up to you whether you would prefer to factor or quadratic formula or whatever. I'm going to factor here. So I'm going to factor using the X method, which is something that I've already done earlier videos on. So if you would like to, be refreshed on that, you can always go back and check out my factoring video. But we'd take our A value of 1 times our C value of -16, and then we'd take our B value of -6, and we are looking for two numbers that multiply to -16 but add to -6. In this case, that would be -8 and +2, giving us factors of x minus 8 and x plus 2. So we would want to set each of those equal to 0 and solve them out to give us our two answers at this point of x equals +8 and x equals -2. Now I recognize that's all been a fair amount of work for this problem, but we're not actually done with this problem yet either. Because remember, anytime we are solving logarithmic equations, we need to plug any answers we find back in to make sure they truly work. We are not allowed to take the log of a negative number. And you can try any calculator you have sitting beside you right now. Take the log of any negative number, it's just going to give you an error back. So we need to take both 8 and -2 and plug them back in to the original equation to see if either of them causes any of our logs to become negative. So we'll scroll all the way back up to the top. And for example, let's start with 8. So we're saying if we plug in 8 to any of these three places, does it give us a negative number? Well, 8 plus 4 is 12. That checks out. 8 minus 4 is +4. That checks out. And 6 times 8 is 24. That checks out. So we now know that 8 truly is an answer to this equation. But we still need to check -2 because it's possible that one also works. So if we come back up here, if I plug in -2 for this x, -2 plus 4 is +2. That checks out. If I plug in -2 here, -2 minus 4 is a -6. That is a problem. If you go try and take the natural log of -6, it's not going to work. So it doesn't matter that it works for some of these logs, it's all or nothing. And since -2 did not pass one of those natural logs, it's not actually part of our answer. Our final answer would simply be x equals 8. Let's take a look at one more example that on first glance does have some similarities to our last example, but will have some key differences in it. We do still have multiple logarithmic terms here, and so naturally we may want to try and make this work for one-to-one property. Right now, there's two logs on the same side of the equation, but a keen observer would notice that there are no logarithmic terms on the right side. And so you may be thinking maybe we could just move one of them to the other side, by subtraction or something like that, and then we'd have a single log on each side of the equation. And that is true, but the problem is we already have this 1 sitting on the right side. It is not involved with either of those logs, which means no matter how we manipulate or move things around, there's always going to be a constant just sitting out there not applying to either logs. And that means that the one-to-one property is never really going to be an option for this equation. If we can't use the one-to-one property, then we really only have one other strategy, and that would be to change from logarithmic form into exponential form. We have already done lessons on that. If you need to go back and refresh on those, you certainly can. But what we would know from those lessons is that in order to change from logarithmic form to exponential, we really should only have one logarithm in the equation. So right now we have too many. This is the part where it gets similar to our last example. We know from our last example, and really from our properties of logarithms notes that we've done in earlier videos, that we can condense or combine these two logs together. Addition in this case condensing to multiplication. Meaning we could write this as the log base 4 of x times x minus 3 equals 1. And now we have a single logarithmic term. So let's go ahead and take x times x minus 3. That'd be a distributive property. X times x would be x squared. And x times negative 3 would be negative 3x. And now, I think we're ready to change to exponential form. So remember, the way this should work is first you want to determine what the base of the log is. The base of this log is 4, so that's where we'll start our exponential equation at, 4. Its exponent would be the lonely 1 on its own on the other side of the equation in log form, and then it would be equal to x squared minus 3x. We have given ourselves, or created for ourselves, a quadratic equation, just like the last example. So again, it's kind of up to you whether you would like to factor, quadratic formula, or complete the square. But we know 4 to the first is 4, so either way, you are taking the equation 4 equals x squared minus 3x and solving it in a way of your choosing. I am going to do it by factoring, but feel free to do it your own way and just skip ahead in the video if you would like. If I'm going to factor, I need to get it set equal to 0, so I would subtract 4 over here, giving us 0 equals x squared minus 3x minus 4, which would mean that I am looking for two numbers that multiply to negative 4 but add to negative 3. In this case, negative 4 and positive 1. So I've got factors of x minus 4 and x plus 1, and I would now want to set each of them equal to 0 separately to solve out, giving me x equals positive 4 and x equals negative 1. For all of us now, no matter what method you use, once you get those two answers, remember we still need to plug back into the original equation and figure out which ones work and which ones don't. Remember, what we're looking for here is to make sure we are not taking the log of a negative number. Well, if we plug in 4 here, that's the log of positive 4, that checks out. If we plug in 4 here, 4 minus 3 is positive 1, so that checks out as well. However, if we plug in negative 1, that does not work for either of these x's. Both of them cause us to take the log of a negative number. So negative 1 does not work, and positive 4 does. One quick side note, I do want to point out that just because the two examples I showed you had one work and one not work, does not mean every equation will be that way. You could have equations where neither of your answers work and it ends up being no solution. You could have equations where both of them work. And yes, you can have equations where a negative x value would indeed still work in the original problem. So do not take those two examples that I gave you to be showing any type of pattern or anything. They are just random examples that I picked because I thought it was useful to show what it looked like for one to pass and what it looked like for one to fail. So I just picked examples where there was one of each. But that is not a pattern and you should not assume anything. You will always need to check both answers.